So my previous videos got deleted because Twitch deletes videos after 2 weeks, which I just realized now. So I realized it might be smart to just make a recap, just make a new video kind of covering the basics of what the previous videos were talking about, which is making a language model that's sort of reading a corpus and learning to predict the next word, learning the rules of the language and learning to predict the next word, and then making a image model that could sort of look at an image and pull out features and use those features to classify whether it was hateful or not. But this video will be about kind of putting those two models together, in addition with some other stuff. So originally I actually put some very basic models together and did some training. I didn't use a validation set, which I'll talk about later of why that's super important. And submitted results, and they were pretty bad, which I had expected them to be because the models were super simplistic and I'm not pre-training them at all. And I had since kind of moved on to starting to develop a more advanced language model, which I'll cover in a video. But that implemented a bunch of techniques that I kind of wanted to go back and use so that I had maybe a better baseline for when I improve the models. So this is sort of me revisiting, combining these models, and so I sort of tweaked some things and tried out some things, which I'll sort of talk about. This introduces a few new concepts. One is I'm using a validation set to understand better how generalized my model solutions are. I'm also using an optimizer in the learning process, which I'll talk about kind of when I get to. But before I jump into all that, I'll kind of just really recap quickly what we have to build to kind of get all this stuff up and running, and cover anything that's different from what we'd previously done. So here I'm just make some constants to where all my data paths are. This image size, I think I redefined this later, but this will come into play later. Here I'm just importing some libraries. JSON lines just lets me open up my training files, and random is just to get a random index. So here, just previously, I'm loading a training set from the JSON L file, but here I'm picking an index to split my training set. And so I'm going to separate out a portion of the data, and I'll never let my model learn from it. And I'll use it as sort of a benchmark to see how good is my model at identifying something as hateful or not, just generally, or how much is it just memorizing the traits of what I'm showing it. So by sort of evaluating the model against a set of data it's never been trained on, I should get a sense of how generalized it is. So basically for me, I'm saying I want a validation set that's 30% of the total training set. So I'm just saying basically give me a start index 70% of the way through, and then I'm just splitting my training and validation sets based on that index. And here I'm also grabbing the test set, which I'll do again later, needlessly, but the test set is a set of data where there's no label, so we don't know if it's hateful or not, and ultimately this is the data set that we're going to use to make predictions on and submit, and the competition will tell us how good we did. So here I just wanted to see how many memes are actually hateful. So if this was an sort of an instance where you had, I think we have 10,000 memes total. If 9,000 of them are not hateful and 1,000 are hateful, the model's very often potentially going to see batches where there's no hateful memes. But looking at this, luckily we can see, it's actually a pretty good mix between hateful and not hateful. So we can assume every batch is going to show the model sort of a healthy mix of hateful and not hateful memes. So just like with the previous natural language model, we have to tokenize things. So we have to sort of construct a way to convert words into numbers and numbers back into words. And we'll create some special characters like before to cover potentially words we've never seen before, with this unknown word, or a blank word, which I'll talk about a little bit later. But you can think of this as just a blank space, a non-character kind of. So here I'm just making a corpus again, and ultimately this is just to determine what are the unique words in the vocabulary that I need to create embeddings for. So the different thing I'm doing here is I'm just uppercasing all the words. So I'm trying to limit the word variance in some way by just converting everything to uppercase, and then punctuation matters a little less. So I'm just here I'm just looking at this corpus and just make sure everything looks okay. So here we're again, just like we did with the last natural language model, we're taking this corpus and we're turning it into a document, which is sort of just this array of tokens, and then out of that we're determining what are the unique tokens, and that's what we're going to use to ultimately build this dictionary that maps. So for every word we see, there should be a corresponding index that we map to. And the numbers ultimately are what we're going to feed into the model and get back out of the model. And here I'm just adding in my unknown word and validating that they exist. So I just want to make sure, okay, that I have entries for these. I want to just take sort of random words. So I pick poop and say, do I have an entry for this? Everything's looking good. I have a couple, so here I'm just storing my indexes because that's ultimately what I'm going to be swapping out. So it's just sort of handy. So the different thing that we're doing here is, so previously with the language model, we had a really small time step. I think we had a time step of like 3. And what we were doing is we were going through a huge corpus and we were saying for every word, predict the next word. And that's a really good task in teaching something the structure of a given language. For us, it's a little more difficult because we're actually looking at a huge stream of memes, and they're not related to each other. And memes can be really short; they could be 2-3 words. So it's really tough to develop a model that's going to predict what the next word is when it's so volatile. It can be so random. But we were trying to resolve these embeddings by going over every word and trying to predict the next word and getting better at that. And we were sort of creating these bunches of 3 words to evaluate. Here we're going to do something different. We're going to turn every text entry. So if we look at what each one of these training entries are, there's an ID, there's a image path to the meme image, and then there's a sentence. And in the case of the training set, there's a label telling us if it's hateful or not. So that sentence, we want to figure out some way, how do we represent this sentence to the model? And we can't give it a random size. So we can't give it a tensor that's 3 words in one instance and 5 words in another instance. So kind of how I opted to represent the sentences is I've determined what's my longest sentence, which I think was like 78 words, which seems like an insanely long meme. But given that sentence, I want to turn every entry into the words of that sentence plus just blanks. So just blank filler characters. And ultimately the model should learn when it sees one of those blank characters that it's meaningless. It really shouldn't have any bearing on whether a meme is hateful or not. So the only thing that should be valuable is any character but this sort of blank character. So I'm going to take the sentence and I'm going to just pad it with this sort of blank index. And so no matter how many words are in the meme, every training item I get is going to be basically this tensor of length. I think I picked 88 for my sentence length, a tensor of length 88. And with the indexes filled in with the words, and then any extra space just filled with this sort of padding character. So that's what this sort of create sentence tensor is. I just sort of am experimenting here to see how is this going to work. But basically, I take a sentence length, so I'm pretty sure this is 88 in this model, and I'm going to get in just some text. So this is going to be the meme text, and then I'm going to get my word to index mapper. And so just like what we did with the corpus, I'm gonna basically create a tokenized document out of this text. So this, in a normal meme, this might have 6, 7 symbols. It's going to be really short. And then I'm going to, for the sentence length, so I know I want to output a tensor of 88. So I'm going to just basically initialize an array with my blank index filled to that length 88. And then I'll just iterate over that document, and I'm going to swap it out for the word index. So at this stage, if you looked at a sentence as the sentence indexes, you'd basically see, for 3 words, it might have ID 1, ID 2, ID 3, and then like we're seeing below, the 7152, which is the index for the blank space. Everything else should be filled with this. So the one thing that I'm doing here to try and be clever, so there's one problem. We have this sentence that we're going to feed into our model, and our model is sort of a recursive model. So it's going to get in a word, and it's going to sort of output a signal, which it'll be combined into the next word, which will output a signal. Because the padding is all coming at the end, it sort of means that it's possible that it might get a really good signal about the meme words and then sort of lose that signal as it's progressing through these 60 blank characters. So here I'm just basically flipping it so that the model is consuming the blank characters first, and hopefully then when it hits a real word, that suddenly becomes meaningful to it. So it's sort of reading the sentence in reverse, if that makes sense. But I'm hoping putting the most meaningful information at the back end is going to help the model better interpret that sentence. So here I'm basically just testing my stuff out to say, hey, let me get some text. So if I actually, hopefully this will work. If I look at some text here, we can see boom, and so here I can create this tensor, and I'm saying here's my sentence length 88. And so if I look at this, I can see, just like I expect, I'm front loaded with all these blank characters, and we can see this blank index is 7152 like we expect. But then at the very end, then we start actually hitting their words. So it's their character, not their color, that matters. And what else? So cool. So anyway, so that's doing what we expect, which is nice. So we can also sort of take a look at the words in here and just verify, as we can see, all those indexes in there are actually mapping to the words that we care about. So the next thing we want to do is create our data set. So we want to make something that we can turn into an iterator, and we can basically say, hey, give me some training data. So previously in the language model, we were getting out a set of words. In the image model, we were getting out an image, which was 3 channels by 256 by 256. Here, we're actually going to get both. So we want to actually, for every entry, we want to get that sentence, which we're going to convert into that tensor of length 88, and then we actually want to get an image, and the image again would just be 3 channels of 256 by 256 pixels. So just like we saw above, here's that create sentence tensor. That's making the tensor and flipping it out of the words. Here's the image tensor, which is coming from the data set that we made for our image model, which is basically just saying, hey, for the training image, let's open it up, let's crop it, not crop it, but let's sort of shrink it to the the aspect ratio that we want. Let's mirror reflect the pixels to sort of pad the image out and make it a square because we want it to be a square. And then turn that into a tensor and return that. So basically, every time we get called next for this data set, we want to return a batch, and it'll be a batch of these 88 long tensor sentences. It'll be a batch of 3 channel by 256 images, and it will be a batch of the actual labels of if that meme is hateful or not. So here on my next function, for when this thing becomes an iterator, I'm just basically filling up the batch before I send it back. So every time this gets called, I'm saying whatever my current index is, let me fill up the next batch full of data and let me sort of poop that back out. So my batch size is 32. I'm basically really riding the line in terms of memory, what I can get away with. So I think anything bigger than this, if I try to increase my batch size or my image size, I run out of memory real quick. So this is basically where I had to settle on. My image size is 256. So this is both the image size and the size of the hidden layers in my natural language model. And I'll kind of they could be different, but I'll kind of talk about why they're the same. So here's that sentence length that I was talking about of 88. So I'm going to make a data set both for training, but I'm also going to make a separate one for my validation set. And here I'm shuffling them both. And that's really just, validation. If I didn't shuffle, I don't think there would be any real difference. I'm reporting validation loss in sort of a dumb way, so it does kind of make a difference for me, but I'll explain why there's a better way to do that. So here I can look at my data sets, and I see that my training data set has 5,900 items, and my validation has 2,500 items. And then I can just take a look at, so I can out of that training data set we have, I can create this iterator, and we can start to look at what's coming out of it when we call next on the iterator, and we can see, just like we were talking about, we get a batch of 32 of these images that are 3 by 256 by 256. We get a batch of our 88 sentence long 88 length tensors, and we get a batch of labels for whether this particular meme is hateful or not. So here is our image model that we built before. I think this is identical. I don't think that I changed this at all. So this is just a basic CNN that has really 2 convolutional layers. So this is really just trying to compress this image into a set of features. And so previously in the image model, we were basically mapping. So we have these 6 channels that we produced, and we were mapping all of the values in those 6 channel matrices to a linear layer that was mapping to 256 features. So this image size is 256, and then from that 256 we were mapping it to 1, which was, is this hateful or not? But in our case, for this model, we actually just want to output 256 features. So our image model is basically going over the image with two sort of multi-channel convolutions that's trying to really extract all the detail out of that image, and then it's basically that's wired up to a really big linear layer that's then compressing that into 256 dimensions. And hopefully what I'm resolving out of the image is 256 different features that the language model can later use to better understand if there's something kind of hateful about the image or not. But so when we call this model, basically we're going to pass it through those CNN layers, which is going to give us back this sort of 6-channel convolution. And then we're basically gonna flatten out those channels, and we're gonna pass it into our linear layer. That's gonna turn it into or here we're just flattening it out, and then we pass it into the linear layer. That's going to give us 256 features back. So how do we combine the language model and the image model? It's incredibly easy. So this language model looks a lot like the previous language model, but I've added some new tricks. But I'll sort of cover those as I go. But the big thing here is you can see our language model now takes an image model. And it's as easy as this, basically, to embed one model in another. I'm just going to hold on to it. So now my image model is basically a set of layers that I can invoke, like anything else. So my embedding layer, my linear layer, these are all layers that I can invoke. My image model is basically the same. And by the nature of tensors, because the output of tensors are feeding into are being used to calculate values in subsequent layers, when I backpropagate, it's automatically going to backpropagate into the image model as well. So every parameter in this model, including the parameters in the image model, will all be trained, which is just a really cool thing to have happen automatically. So I have an embeddings layer. This is to take to map the word into a stored embedding. And this hidden size, I'm keeping the same as the image size, so this comes out as 256 as well. I don't need parity. I think it's just convenient to kind of keep everything the same. My hidden layer is sort of my recurrent network. So for each word in the sentence, which is going to be 88 words, I'm going to keep passing it into this linear layer, keep passing the output of this linear layer back into itself. And sort of developing some context about what the meme is about. So this evaluator, so this linear layer is going to take in, as the recurrent process happens, this is going to output basically 88 outputs. So previously, in the context of trying to predict the next word, you would say 88 predictions. This isn't really trying to predict the next word, but it's basically for each word, it's producing an outputted signal, and the signal from the previous word feeds into the next one. So it still has this concept of sort of a rolling context, but it's not trying to predict a word. It's just trying to sort of output a useful set of information about that word. Hopefully that makes a little more sense as we go on, but so that's sort of feeding back into itself, this hidden layer, and then this evaluator is saying, hey, now I have this stack of 88 signals that you've made from all these words. I'm going to flatten them all out, just like I was kind of doing in the CNN layer. I'm basically just going to say, okay, I want to listen to all this stuff, so I'm just going to flatten it all out. But then I'm doing one thing where so normally I would just multiply it by the time step, which is 88. So normally 88 words should be coming out of this thing, so it's the stack of 88 entries of hidden size of 256. And so I'm just basically going to concat them all together. But I'm also going to concat my image features on top of this as well. So in addition to the time set, which is 88, I'm saying add one more 256 entry, because I'm actually going to map my image features to this. And then I'm outputting 256 again. So I'm basically evaluating this whole thing, and again, I'm turning it back into 256 dimensions. So dropout, I use a few places. So dropout is a layer that you give it a percentage. So I'm passing in this dropout percentage. For me, I'm using 50%. And basically what it does is whatever data I pass through there, it will randomly, it's not truly random, but remove that percent. So you'll see later, whenever I pass data into this dropout layer, it's just going to randomly zero out 50% of the data. And you might think, I want a model to train better, so of course I want to give it the most data. Why would I randomly remove data from it? But I'll talk about kind of a little bit why this is a super powerful thing that you can do, and why it ultimately makes your model much better. And then finally, we have this output layer where I'm saying, given this hidden size, which is 256 dimensions, I ultimately want you to just resolve it to 1, which is, hey, is this thing hateful or not? Arguably, I don't need this. I think maybe I should just be mapping the evaluator to 1 value, and that this sort of reduces fidelity unnecessarily, but I'm doing it for now. So here, the sigmoid, I basically, I'm going to do binary cross entropy as my loss function, and that's expecting a value between 0 and 1. So sigmoid's just going to collapse. Whatever value is outputted from my output layer, it's just going to collapse that into 0 and 1. And here I'm just holding on to my time step. And this is 88, so this is that sentence length, which is a gigantic time step. Actually, I should qualify that. In terms of RNNs, an 88 length time step is really insane. So this is probably not the best model I could be using. So here's our forward pass for the model. So this model is gonna get an image. It's gonna get a sentence, which is that 88 length tensor. And then it's got this evaluate flag, and I'll talk more about this when we get to validation sets, but this basically cancels dropout. So if I'm in evaluation mode, I actually don't want to remove any information. So like our previous language model, we sort of have this stack of outs. So these are the sort of output signals that the RNN is going to accumulate as it's going through every word in the sentence. But the interesting thing, or maybe not interesting, is so in our previous RNN, we were using an internal state that was preserved between words. So as something was reading, as the model was sort of reading through a length of words, it was holding on to an internal state that was helping it better contextualize what was happening word to word as it moved through a sentence. So for us, we're not holding on to a hidden state. Rather, we're initializing our state to be the feature output from the images. So I don't have a great explanation for why I'm doing this other than just some bad intuition, which is the first thing, if I think about interpreting a meme, the first thing I do is I look at the image, and then I read the meme, and then I probably look at the image again. So the image helps contextualize the words, and then the words help contextualize the image again. So I'm trying to recreate this mechanism in a really hacky way. And so the first thing I'm trying to recreate is that initial sort of context set of looking at an image and resolving the features out of the image that I think could potentially be hateful. So that's basically what I do. Is this X, I'm saying, hey, let me take that image and let me pass it through my image model, and let me get a feature set back of 256 for every item in our batch. And then if I'm not in evaluation mode, so if I'm training, I want to just randomly drop some of this data out. And so dropout is really nice. So when I originally built this, I had no validation set, nor did I have dropout or really any regularization techniques in my model. And so what happens very quickly is that your model just memorizes the images in your training set that are hateful. So it doesn't learn the general idea of what makes things hateful or not. It just immediately memorizes all that stuff. So after I built the model and I tested it, of course it did terribly. I think it got like 53% accuracy, which I was surprised even by that. I have to assume that's within the margin of just random error. But the reason is because it had sort of overfit, they say, to the training set. I had not made something that was generalized. And if I had been evaluating my model against a set of data that I wasn't training with, I would have realized that right away, but I was just kind of putting it together and getting it out. But this dropout helps prevent that memorization, and it does that by sort of randomizing the input. So it create, I don't want to say infinite variations of your data, but it creates just a huge magnitude. So in our case, we don't have many examples. I think we have in our training set, we have 5,900 examples or something like that. But because we're randomly dropping 50% of that data out, the configurations that the model is ultimately seeing is like it exploded. So the variance in data it can see, and you could kind of get a sense of if you were shown the entire picture of a tree constantly and kind of learn to recognize a tree, you would be learning to recognize the entirety of the tree, because that's really the only example you had. But if you were instead shown pictures of trees that just a small portion of the image, or just half the image like was just missing, you would start to have to understand what are the true features of trees. So I'm not just sort of memorizing this tree in its entirety, but when I see these types of things, how do I learn that that's a particular thing? So that's kind of what Dropout is doing, is that I don't want to say it's like turning your data into an infinite data set. That's not really what it's doing, because it's definitely never going to show you anything you haven't seen before. But it's creating such a high variance of your data that it helps the model better generalize, which means that as it gets better evaluating whether the training data is hateful or not, it can effectively apply that to the validation set. So I basically, the image, I want to do that. I want to sort of remove some of the detail out of it and create more variance and potentially how these images are interpreted by the model. And so then, just like the previous natural language model, I'm sort of going over my time step, which is this 88. I'm grabbing each individual word out, which is just the index of the word for that whole batch. And then I'm adding that to the outputted embeddings for that word. And then I'm just doing ReLU. So if there's any negative values, I'm just canceling them out. And then I'm appending that. And I'm just basically, so then that X gets fed back into the next set. So it's been seeded sort of with the context of this image, but this rolling context ultimately hopefully preserves the information out of that image that's relevant. And the likelihood is that for like 70 time steps, this thing's just going to be hitting that blank index. So what I'm hoping is that the blank index embeddings are like one, basically, like an identity function, that they don't actually change the value. That's what I'm hoping. I don't actually know if that's what's occurring. So the last thing that I do after I've sort of created the stack of outs, which are all these signals for each individual one of the 88 tokens that it's seen, is that I append the image back in. So the image was the context, but I also want to provide the image as a signal to the evaluator, or the image's features as a signal to the evaluator. So I'm going to basically append that on, and that's why I had to do this time step times 1, because I'm basically saying I'm going to have a stack of outs that are linked time step, and then I'm going to add one more, which is the image. So here I'm just converting that into a tensor. And again, if I'm not evaluating, I'm going to just randomly drop a bunch of this stuff out before I show it to my evaluator. And my evaluator is basically doing kind of like what we saw with the CNN. It's taking the 88 signals plus the image features, and it's basically just concatenating them all into one huge long tensor and passing that into our evaluator, which is giving us back 256 features that hopefully now the final output can use to determine if something's hateful or not. So here on my output, I'm basically converting it to one single value, which is, are you hateful or not? And then I'm normalizing that between 0 and 1. So hopefully that was obviously a lot of stuff, pretty quick. But it conceptually, basically, I'm sort of setting some context from the image. I'm gathering a signal output for every word in the meme, plus a bunch of blank characters until it's padded to 88. And then I'm adding my image features onto that stack so that my evaluator can also look at the image. And then I'm passing those out. And then I'm using Dropout for my image and my language signals to create some additional variance. So the evaluator has a more more representations of the data in terms of what's hateful or not, and it can hopefully learn a more generalized solution. So that's it. That was obviously a lot. I'm assuming that was probably difficult to understand because I'm a terrible explainer, but basically we can make our image model now. So just like we saw, we make our image model, we give it a size. And then this vocab size, we need to know this to know how to size our embedding layer. So we just get a length of our word dictionary. Here we're going to set our dropout percentage, which is 50%. So half of all those activations to just be zeroed out. And now we're going to make our language model, and we're going to pass it our image model. And we're calling CUDA to throw this thing on the GPU so that it doesn't take forever to train. So here we can test the model. So if we, like we saw before, if we call our iterator, we see some input images and sentences and targets. And we can call our model now, so we can pass in those images and the sentences, and we're going to get a set of predictions back. And if we just look at those predictions, we can see it's what we want. It's we passed in a batch of 32, so we got 32 predictions back. And if we actually look at some of those predictions, we can see it's a value between 0 and 1 is what we expect. And these are basically random values at this point. So that's basically all we needed in terms of getting the data set ready. So now we have this data set that we can call, and it's going to give us a batch of sentences and images and the hateful or not label. And we have this model we can pass, basically we can pass a batch of images and a batch of sentences into, and it will give us back predictions about whether something's hateful or not. So this is our training loop. And so this is a very low learning rate, this 1E7, because I just finished some training, but I think I started at like 3E-4. So weight decay, I'm going to talk a little bit about, so I have really sparse data, which is a really tough problem to use a limited amount of data and come up with a generalized solution. It's very difficult. So generally what you do is if you want to have a more generalized model, you show it more data. So the more data you show a model, the better it'll get. But there's this problem of, there's instances where you just might not have a lot of data. And so memes is kind of a interesting use case where you can imagine if there's a new meme that's sort of hateful and it's sparsely represented, you still want something that's sort of be able to detect if it's hateful, especially if it's new or something like that. You could have a new hateful meme spreading that you want to be able to detect against a low amount of data. But overfitting is this huge problem because it just can't look at enough data. So it sort of wants to gravitate towards just memorizing the features in your training set. So there's a few techniques we can use to prevent that, and one of them is dropout, which we saw. So we're going to try and create more variance in the data by just sort of randomly dropping things out. But this other thing that we're going to do is we're going to introduce something called weight decay. And the easiest way to think about weight decay is, so we compute a loss by how wrong we were in terms of our prediction about something being hateful or not. But we can also add, values to our loss sort of arbitrarily. And one value we can add to it is we can add the weight of the tensor connection to the loss. So we can say, actually, in addition to how wrong I was in my prediction, I also want to add up all the weights in my model and multiply it by some number. And so here I'm multiplying it by 0.192. And I want to add that to my loss. And why would you do that? So first, it's kind of important to know why having high weights would be bad. So high weights generally signal that your model is like hyper attuned to one specific feature. So it has a weight that's really high, so that when one signal comes in, it activates really largely, and it has sort of this outsized effect on the model. And those types of connections are really good at like memorizing what's hateful within a feature set, because you can basically figure out what are the discrepancies between the images that are hateful and let me hyper attune to them. So let me activate really largely when I see them. And that'll make me better at predicting whether the training set is hateful or not. But that's actually not what we want. We don't want it to actually attune to specific features of the hateful images and really react to them largely. What we really want is we want a very combinatorial reaction where many weights are interacting with each other to sort of ascertain the subtle patterns of what we're looking for. So that's what we ultimately want to optimize for. So by adding all the sum of all your weights to your loss, you're basically saying, I don't want my weights to be large, which sort of punishes weights that are getting too high, and it forces weights to get lower. And so forcing weights to get lower and achieving the same result means that they, like I just said, they kind of have to act in a more combinatorial way, which should better reflect the patterns that we're looking for. So that's sort of that's my intuition of it. And in this case, it's very effective against in regularizing our data. So we use weight decay. We also use an optimizer. So previously we were just going through our training loop and calculating loss dot backwards, and we were multiplying the learning rate by the gradient manually. But that's kind of a ham-fisted way to update your gradients. If you think, what would be the optimal way to determine what the right, or not gradients, but the weights. What's the optimal way to determine what the right weight is? I could definitely just say, hey, whatever the gradient was, multiply by the learning rate, we're good to go. But also we could say, if I look back previously, what was the change? How fast am I moving, basically? Am I moving really fast in the right direction? Then maybe I should have a higher learning rate. Am I moving really fast in the wrong direction? Maybe then I should have a lower learning rate. Am I moving do I keep switching around a lot? Maybe then I should have a lower learning rate. So by looking at what the previous changes in the data are, each parameter can ideally figure out what its own optimal learning rate is, versus just taking the supplied learning rate and using it for every single parameter. So you can utilize something called an optimizer, which is basically going to kind of do this for us. It's based on some heuristic. It's going to figure out how should I adjust my learning rate based on how much I've sort of changed previously. And one popular optimizer is Atom, and I think these optimizers really the big difference is that they're sort of looking at different sort of rolling averages or different gradients of gradients or things like that. So I think they're sort of complex in how they're trying to evaluate the trend of the learning rate and ultimately what subsequent learning rates should be. But they're a really super handy technique. So now, instead of just sort of clobbering every learning rate or every parameter with the same learning rate, we have something that's a little more refined, that's going to keep an eye on kind of how that how the gradient and the parameter are changing, and sort of try to adjust the learning rate to maybe make it move in the optimal direction at the optimal speed. So here I was doing 50 epochs. This is really at the end of my training. And so if we go through our training loop, so I'm using the optimizer, but there's not a lot different. The two different things are here I'm zeroing my gradient out, which was actually something I did previously after I updated all my parameters. And then I'm calling this step function. So this step function, I'm pretty sure, I'm not 100% sure, but I'm pretty sure that this is internally then calculating what the new learning rates should be. So I'm doing this for my training set, but then after I finish going through my training set, I want to go through my validation set and look at my validation accuracy. So here I do the same thing, but here I don't actually want to. I don't want to calculate. I don't want to back propagate. So I don't want to actually train from these predictions. I want to keep the model blind to these in terms of training, and just use them as a benchmark for how well it's doing. So I'm still doing the same thing. Now I'm getting images and sentences out of my validation iterator from my validation data set, and generating some predictions and calculating loss. Here I'm calling detach so that I can just sort of detach from all the tensor connections, because I don't really care about how this loss was constructed, because I'm not going to back propagate. So here I'm converting my tensors into NumPy arrays, and NumPy is just a library to work with matrices. That's pretty handy and really common. And so I'm going to do an accuracy predictor that's expecting NumPy arrays, which is why I have to convert them. So I'm basically going to take all my predictions. I'm going to throw them on the CPU, because right now they're on the GPU, and I'm going to round them. So I only care about a value between a value of 0 and a value of 1. So 1 being this is hateful, 0 being this is not hateful. And so I'm going to round it to get those values, and then I'm just basically going to say how accurate I am. And so this was a ton of training, and not a ton, like a day. I mean, not really anything meaningful, but previously when I was training this, I would have really low training loss and really high validation loss, which is sort of classic for overfitting. And so I was playing around with weight decay and the correct dropout percentage. So there's definitely a lot of tweaking in this model that I had to do. But ultimately I got something where the training and validation losses were pretty similar. And here, when you look at my accuracies, like, it's not amazing, but it's not super terrible. So one stupid thing I'm doing here is that these losses are just the loss of the last batch, and the accuracy of the last batch. So what I really should be doing is adding all these things up and averaging them, but I was too lazy to do that. So these are all over the place, but I assumed I can get a sense of how it's doing by just how frequently I'm seeing the same numbers. So basically there was a lot of tweaking. Weight decay and learning rate, and trying to figure out, can I sort of settle on something that's generalized well. So this thing seems to have generalized well against the validation set. Whether it has generalized well against the test set is something to totally be determined. So I basically ran all those trainings. This last one has me a little spooked, but I definitely have seen 46%ers before. So once I finished training all this stuff, I just wanted to save it. So a lot of times, you'll be training and you'll like run out of memory, and you'll have trained a model for 20 hours and you'll accidentally do something stupid to run out of memory, and then it's gone. So periodically saving your model is really nice. Torch makes it super easy. I think this uses Pickle, which is just like a Python serialization library under the hood, so I don't think there's anything special. Your exact class at least in the context of Jupyter Notebook, your exact class definition has to exist for this thing to work. So if I went up here into my model and I changed a bunch of stuff around, I could no longer load that model, which is kind of a hassle. But here I was just sort of testing how accurate is my predictions. So here now I can actually evaluate the test set. So this is really, the proof is in the pudding. I can look at my validation set and pat myself on the back if it seems okay, but really it's the test set that we care about. So I'm doing a lot of copy paste, where I'm loading in my test set, and I'm basically doing the same thing in terms of creating sentences and images. The only thing different is that instead of returning a label, I'm actually going to return the ID of the entry, and that's what I'll use ultimately to update, to create my CSV file of IDs with the predictions that I can submit for the contest. And let's see here. And yeah, so that's so I'm basically just outputting a bunch of IDs and just make sure everything's okay, and that I can make predictions against this test data. Everything looks good. So here when I'm generating my predictions, so actually we can I can maybe start to go through this. So one really annoying thing is that the IDs have to be in the exact order that that they're supplied. So the first thing that I do while this thing's running, the first thing that I do is let's just make sure this works. Boop, boop, boop. Cool. So I'm gonna just create a results dictionary, and I'm just gonna go ahead and populate all the IDs so that they're in the right order that I can update. So I do 3 epochs, and the reason I do 3 epochs of the test set is because there's the sort of batch number doesn't line up with the amount of items that I have exactly. So if I just ran through this once, what I would have is like just a small, like less than a batch at the end that had no data. So by doing 3 epochs, I'm shuffling the data and making sure that I've basically covered it all, just through brute force randomization. Boop, boop. So that's going to go through. That's going to predict their stuff. Take a look at some entries. So here we're going to create a results list. We're basically just going to create a CSV file. So I'm creating my CSV header and my length, and we can see we have what we expect, which is 1,000 entries and 1 header. And so here I will save this, and let's just verify that we didn't actually, I don't have any negative ones in here. Okay, looks good. Okay, so now I think I can go over here, which I don't know if you can see. I doubt it. Okay, cool. Sorry, that was a long pause. So I just submitted. And I don't know if I can actually see the submission. So my highest was 53. That was actually the first one that I did. So I was very hopeful about this submission. But as you can see, it's actually, let me make sure you can see that. You can 49.15. So that's pretty terrible. So accuracy 49%. So worse than a random guess. So there is some difference. This initial submission was just using a more advanced language model. But what this is really telling me is that even though I had regularization techniques that were keeping the loss relatively stable between my training and validation sets, that didn't actually apply to the test set. So this was false confidence. But that's good. So we sort of have a baseline. We know, we did a bunch of funky stuff. We improved our regularization and sort of still had a terrible model. So the next video I'll make is using a much more advanced language model, which I think is going to produce much more interesting results, and better regularization techniques that hopefully help us sort of kind of better understand or have a model that's even more generalized. We're gonna beef up our training data by using Google Translate, which is kind of an interesting technique, and I'll explain that more then. And we're going to start to use pre-trained weights. So this thing's pretty terrible, but I think we're sort of on the road of getting there. This is a good experiment of just combining these models and ultimately seeing what they can do. But I think the true power will be when we actually use more impressive models to evaluate this data. So that's basically it. Hopefully that was kind of interesting and not super confusing. Bye.